Hey, what's up? Today we're talking about stratigraphy, which is actually the art of determining the ages of rocks and fossils. And that's important because if we can understand the age of the Earth, then we can understand a little bit of the story about our Earth and where it started and where it's come and how far it's come and maybe where it's going as a result of uniformitarianism, right? If we can understand what's happened in the past and we can still see those processes happening today, then it can help us predict the future. So we use stratigraphy, which is basically using rocks and fossils to help us determine the age of the Earth and using the Earth and her processes to help us determine the ages of rocks and fossils. So we know that relative dating compares things to each other and ages things based on oldest versus youngest. So that's just a comparison thing. Like I am younger than my grandma and you as my student are younger than me. That is relative dating because we're looking at how old we are, youngest to oldest, based on how we are in relationship to each other. Absolute dating, on the other hand, gives us exact years or exact periods of time based on chemical studies and other scientific studies that can give us really more specifics, right? So not so much these rocks are older or younger than these, but that these rocks are 120 million years old, whereas these down here are 140 million years old. Okay, so back to talking again about uniformitarianism. It is this idea that we believe that natural laws worked the same in the past as they do today, like I mentioned earlier. It helps us to make some inferences about the ages of rocks and fossils and helps us to understand the past and prepare for the future. Because the deeper we dig, the farther back in time we see. And we can see maybe where the Earth is going based on where she's been. Back to this, you've seen this before. This is just showing us the processes again of the rock cycle and just how the Earth's age cycle works. And the idea that these processes are happening now and they happen the same way in the past. And again, that's more uniformitarianism. So the first principle of stratigraphy is the law of superposition. There are three principles we'll talk about. This is the first one. Law of superposition is a way to use how rocks are layered or how they're put together to assign an age to those rocks and any fossils that are in these layers as well, because sometimes fossils are caught up in the sedimentation of rock layers. Law of superposition says that the layers are laid down in chronological order. So the older layer is at the bottom and the youngest layers are at the top. So as we go from top to bottom, we get youngest to oldest, and we get older and older and older as we go down, whereas the very oldest is on the very bottom, the youngest is at the very top. And this is the law of superposition. Now, the law of superposition works great, but it only really works on rock layers that are undisturbed, meaning that there hasn't been any kind of upheaval or change in those rock layers. They've just been laid down and they've just sat there without any kind of problems or issues. But we know because of things like faults and rock folding and earthquakes and volcanic eruptions that rock layers do get disturbed. And so that messes up law of superposition. We can't use the law of superposition when those things have happened. So when they have been disturbed, then we use fossils to help us determine what the ages of rock layers are and what their stories are. We use something called index fossils to determine this. And this is actually a picture of a trilobite. It is a great index fossil. It's super useful for dating and organizing the layers where it's found. It can tell us how old the layers are that it has been found in. And it can also give us information about the layers beneath it and the layers above it. And so fossils that work that way are called index fossils. And this trilobite is a good example. Index fossils are really specific organisms that are used to help us mark periods of time in geology or in rock layers. We have a couple of examples here. We have the Cenozoic era, the Mesozoic era, and the Paleozoic era. And in these areas, we see some really good index fossils. These are good examples of index fossils. And the reason they are good is because they have these important characteristics. We know that index fossils are found in many places throughout the earth. So they're not just found on one continent, they're found in multiple continents. And that helps us a lot. That means they're uniform throughout the earth, and also give us an argument for Pangea by demonstrating that fossils are found all over the earth, even though those continents are not close to each other anymore. Number 2, they fossilize well. They're easy to recognize. So that means that they don't just dissolve. Like plants are not always great fossils. Soft tissues like fur and skin, these are not good fossils. Wood's not always a great fossil. These are things that degrade in relatively short periods of time, and so they don't stick around. They don't end up fossilizing well. But things like shells, exoskeletons, sometimes bones can be really great fossils because they are preserved well and they're easy to recognize. And then finally, number 3, they live for a really short period of time. Index fossils are here for a very specific short period of time, and then they go extinct. And so they help us to zero in on that specific period of time because we know they were only here during that period of time. So if we see a specific fossil in a layer, it tells us about when that layer was laid down, because we know that that fossil lived for a very specific short period of time. So if that fossil is in that layer, then that layer must come from that period of time. So those are the 3 characteristics of index fossils. So if we look at these examples here, we have one on the north, one in the west, east, and then south. And we see fossils in each of these sections of layered rock. We want to look for a good index fossil, and we have to keep in mind those 3 characteristics of index fossils as we choose. So if we look at fossil 1, fossil 2, and fossil 3, and we think about those characteristics of index fossils found in many places throughout the earth. So do we see a fossil here that's in many places? Well, we see this fossil 3, and this fossil 3, and this fossil 3. But we don't see fossil 3 here in the west. We do, however, see fossil 2 in the south, the west, and the north. And we see fossil 1 in the north, the west, and the east. Now, if we go back to our characteristics, are they found in many places throughout the earth? Do they fossilize well or easy to recognize? And do they live for a short period of time and then go extinct? What fits all 3 bills? Well, we can see that all 3 of these fossils fossilized pretty well. So number 2 is taken care of with all 3 of these. We see that fossil 1 didn't live for a short period of time. It kind of hopped around, and it wasn't consistently in the same period of time every time we see it. It's actually found in 3 different periods of time. So fossil 1 is probably not very good because it's found in 3 different periods of time. Fossil 3 is also found in different periods of time. So that's a little bit confusing because we're not seeing that it's found consistently. Fossil 2, on the other hand, is a pretty good fossil because we find it consistently in the same limestone B period of time. So that helps us really zero in on fossil 2, helps us to understand a lot about this limestone B section because we see fossil 2 there consistently. Fossil 2 is easy to recognize. It may not be in the east section, but it's nice and consistently found in the northwest and south sections. So fossil 2 is our best index fossil here. Knowing the relative age of index fossils in one location can help scientists infer the relative age of fossils and rock layers in other locations. So we have these layers laid down in Montana with the younger rocks near the top and the older rocks in the bottom. We have similar layers found in Texas, about 1,200 miles away. And we can see similar index fossils in similar layers in both places. So even though these layers are found very far apart, we do see this index fossil turning up in both places. And notice that they're turning up in the same type of layer of rock. So that gives us some really good information about both of those places, as well as those fossils that are found in those places, even though they're found pretty far apart. This slide just shows another few really good index fossils. You can go through these and read them and get some good ideas on some of these good index fossils. These are real fossils that we use in the study of relative dating of the Earth's age and layers of rock. And you can check those out and use them as examples. So back to talking about that law of superposition, the one that talks about how the older rocks are at the bottom, the younger rocks are at the top. A couple of things that can eliminate the use of the law of superposition. Remember, it only works with undisturbed rock layers. So what types of things eliminate the use of the law of superposition? Well, if we have inclusions or pieces of rock that are included in sediment that don't originally belong there, that kind of messes up with the law of superposition. If we have intrusions or lava flows inserting in between lava or layers of rock, that kind of messes up the law of superposition because it's out of order. If we have bending and folding or faults where we have layers bending, folding, snapping, shearing, that really is going to mess up the order of the rock layers. So we can't really use law of superposition in either of those cases. And then finally, if we have an unconformity, which are places where we see that something happened, but maybe we can't see why because of erosion or something. So we don't understand, there's missing information. And that means we can't really use the law of superposition either. Let's look at some examples. This page is really great for that. I'm going to have you go ahead and go over that on your own. There's lots to read here, but it's really good information. It talks about what an intrusion is. We have examples here and here. It talks about maybe some bending and folding. We can see here. We can see some faults where we have shearing and breakage in layers. And we have an unconformity where we have something that happened down here and something that happened up here, but there's some missing information here along this line. So just go ahead and check that out, get a little bit more information. We also have what's called the law of included fragments, or the law of inclusions. The law of included fragments just says that fragments of one type of rock are found in another type of rock. I like to call this the chocolate chip cookie law, because if you think about it, you can make chocolate chip cookies and the chocolate chips are part of the cookie after it's baked. But before you bake that chocolate chip cookie, the chocolate chips exist separately. They're older than the cookie itself. So even though you have the chips in the cookie, the chips themselves are older than the cookie because they existed before the cookie was baked. That is like the law of included fragments, meaning if we see pieces of rock included inside of an older rock or a younger rock, we know that those fragments that are included inside that younger rock are definitely older than the whole rock itself. So let's check out unconformities. Unconformities are where we have a break in time. This is a really good one because we can see some really distinctive gray shale layers here. But then all of a sudden, and they're sort of jutting off into a diagonal direction. All of a sudden, though, we have these straight, different colored layers just above that. We know something happened along this line, and we call that an unconformity. We just see a big difference in the type of rock, in the direction that it's layering. Something happened there, and the evidence of it is missing. Maybe it was eroded away, maybe lost in a landslide, something like that. But we can see some consistencies below and some consistencies above. We just have this missing piece here, and we call that an unconformity. That also disallows the law of superposition. These are some different stages of unconformities. We'll have an initial deposition, like a regular sedimentary rock layer, or set of sedimentary rock layers. And then maybe we'll have some deformation because of like maybe some folding and bending because of an earthquake or something. After that deformation, we might have these folded layers sit in this position for a long time, and so the tops are all eroded away. Suddenly it looks like level A is maybe the youngest rock, but we know it's actually the oldest because it's at the bottom and it's just been folded and bent. And then we'll have some new layers deposited on top of that eroded away, bent, deformed rock layer set, and they'll lay down straight across just like the original deposition. So that's kind of how an unconformity works and maybe what could happen in the story of the life of an unconformity. Our last little law, we already talked about the law of superposition, the law of inclusions or included fragments. Finally, the law of cross-cutting. The law of cross-cutting just says that we can have our layers where we might use law of superposition, but if all of a sudden we have a layer randomly cutting across these layers, like layer F here, or up in this picture, layer 4, we know that the layer that is cutting across is the youngest layer. So we can see that all the layers that F is cutting across are going to be older than layer F. So like layer B, C, D, and E are all older than layer F. But layer A is younger than layer F. In this example, layers 1, 2, 3 are all older than layer 4. It is younger than them. But then layer 5 is younger than layer 4. So that just kind of shows us the law of cross-cutting, where the layer that is cutting across is younger than all the layers that it's cutting across. F is not younger than A because it's not cutting across A. And 4 is not younger than 5 because it's not cutting across 5. But it is younger than all the others. So to sum it all up, we have our principles of stratigraphy, the law of superposition, law of cross-cutting, and law of included fragments. We have a great example of law of included fragments here, kind of a chocolate chip cookie analogy. We have a good picture showing law of cross-cutting here, where we have that youngest layer cutting across all the older ones underneath it. And we have the law of superposition, with the youngest layers at the top and the oldest layers at the bottom. Go ahead and check out this video in your slides in Canvas. It kind of goes all through this again. Use what you know to put these events in order in your worksheet. Here's some examples of those principles and relationships. Layer these from youngest to oldest with A all the way through to E, which is youngest, which is oldest. And then on this slide, you have a game you can play called Layers of Time. In order to complete your worksheet, you'll need to play the game, take a picture, and insert that picture into your worksheet. And finally, do you know the absolute age of person C? You probably don't, but you definitely know that person A is the youngest, person B is the oldest, and person C is in the middle. We can't get the absolute age, but we can definitely get the relative age. And that's what we're doing with Layers of Rock. Go ahead and complete your worksheet, get it submitted, and we'll get it corrected for you. Thanks a lot.